So here I am picking back up the Starting Materials and Polymerization Methods lecture. This is the second video of that lecture. So to recap, in the previous lecture we talked about chain growth polymerization, which is often referred to as addition polymerization. These terms are often used interchangeably. Also, step growth polymerization is the other polymer synthesis type, and this is often referred to as condensation polymerization. So you'll often hear chain and addition used and step and condensation used interchangeably. There are exceptions to this, but most often chain growth polymerization is addition polymerization, and most often step growth polymerization is condensation polymerization. Step growth polymerization is a little more complicated than chain growth. So in chain growth, you're just sticking one monomer to the end of each chain. There you have it. Step growth is a little more complicated. So in step growth polymerization, you have a small molecule byproduct. So you give off something like water or methanol or something like that when the two ends of the chain come together. And that's also why it's called condensation polymerization. You condense a small molecule, you condense water from the reaction. These are relatively slow reactions. You don't need an initiator for them. You often use a catalyst, because when I say slow, these can go on for days. I've done step growth polymerizations or condensation polymerizations that have lasted for 3 days. So they are very slow compared to chain growth, which can happen in a matter of seconds. I've also done chain growth polymerization that has been catalyzed and completed in a matter of seconds. So the reason why you do step growth versus chain growth, though, is you can't get certain polymers from any other way. So in step growth polymerization, this occurs in steps. So first a monomer reacts with another monomer to create dimers. Then you get trimers that form, and then longer oligomers, and then eventually long chain polymers. Monomer disappears very early in these reactions, and you have kind of a whole bunch of dimers, trimers, and oligomers, and then you don't get high molecular weight polymer until the very end of the reaction. So you have to have 99% or 98% conversion and higher to get actual polymer from this. So you really need long reaction times to build that molecular weight up to where it needs to be significant. So here are the characteristics of step growth monomers. The monomers must be bifunctional. And this always confuses people, so I'll try to explain this the best I can. So you have to have, there's two types. There's AABB, and then there's AB. So for AABB, here you have so many numbers of AA monomers. A can only react with B. So this can't react with itself, so you have to react with another B monomer that's present. So in this case, the AABB type of polymerization are always copolymers. There's always two different types of monomers there. So this is the structure that you get in the resulting polymer. So in this case, this A is always followed by B, and then this B is always followed by A. So this is always a copolymer. Now in AB monomers, A can only react with B. So one end of the molecule has an A on it, the other end of the molecule has a B on it, and that gives you this particular repeat unit. So these are both linear polymers. If you want to branch or you want to cross-link, then you need to have higher functionality. So here we have 2 A groups, here we have X with 3 B groups. So A can still only react with B, but A can react with another BB monomer, or it can react to create these branch points. So all of this A and B, that's just fine, Gene, but what does this actually mean to me? So this is what it means for actual step growth polymerization, and this is why we still do step growth polymerization even though it takes so long, is because you can't get polyesters or polyamides, in other words nylons, or polyurethanes any other way. So polyesters have 2 dicarboxylic acid groups, that's what these are, and they react with an alcohol to create a polyester. So when we're talking about step growth polymerization, we're talking about multiple or polyester bonds that are formed between a carboxylic acid and an alcohol. So this creates a polyester, and this is your repeat unit. Now this is a good time for me to point out something when you see these brackets and this N. If you see these brackets and this N on an exam, this is a polymer. So if I ask you, what is this structure? It needs to be poly something. Don't give me ester, don't give me alcohol, give me poly something. It needs to be a polymer. So if your only choice is a polymer on that list, that's probably the right choice. So moving on to polyamides, here, so this is our AA, this is our BB. They're kind of arbitrary. You can call this BB if you wanted to, but there's 2 groups here. This carboxylic acid can only react with that hydroxyl group. on the alcohol. So here we have, here's our AABB. So again, this was a A over here, it's a B over here. This is a dicarboxylic acid, and that's how you make a nylon. So in this case, we refer to them as nylons commercially, but what they're actually known as polyamides. And so this is an amide bond, shown here in the red. So this is a polyamide, or multiple amide linkages being created. Again, we have brackets and we have an N, so it's a polymer. So this amine can only react with this carboxylic acid to form an amide bond, and that's where we get this. Now, in most step growth polymerizations, you condense a small molecule. In this case, this is water. It's water in this case as well, so there should be plus water and plus water over here. Polyurethanes are step growth polymerizations, and that's, you have a diisocyanate and a polyol. But these don't condense a small molecule, so they are step growth polymerizations, but not condensation polymerizations. So there's an exception to every rule, and that is the exception in terms of polyurethanes versus other step growth polymerizations. But here we have AA, which is our diisocyanate, so this is our A group, that's an A group. This is a B group, BB. So again, dialcohol, but they form different linkages when you react them with different things. So this is just an example. Now there are different methods. So you can do free radical, or you can do chain growth polymerization, or you can do step growth polymerization. You can do both of those in the bulk, or solution, or emulsion, or suspension, or gas phase. So this is different types of reaction setups in order to polymerize. So there are different factors influencing the choice of polymerization method. Sometimes it has to do with monomer reaction chemistry, the toxicity of the monomer, the flammability of the monomer, the odor of the monomer. Monomers are small molecules. They are flammable chemicals. They are toxic. You should not drink them. I often use this example. Styrene will kill you if you drink it. If you eat a polystyrene packing peanut, it might cause abdominal obstruction or give you a bellyache, but it probably won't kill you. So monomer versus polymer, styrene versus polystyrene, they're very different in terms of their chemistry, toxicity, things like that. Also, when you polymerize, you create heat. So you have to figure out a way to remove that heat, or you can have problems. And then, what's cost effective? Now you can polymerize vinyl chloride in the bulk, but in the US, most polyvinyl chloride production is done by suspension. And we'll talk about the pros and cons. So, you know, if this is cheapest, what this tells me is bulk polymerization of vinyl chloride monomer is not the cheapest. In other words, suspension polymerization for all steps involved is the cheapest method of PVC production. So, we're going to compare heat removal, viscosity, purity, and conversion level for each of these processes. Bulk polymerization, it's simple. You have monomer, catalyst, polymer. And at the start of the reaction, you have monomer and catalyst. Those two things together in a reaction vessel, and you stir them at a particular temperature. And for bulk polymerization to work, the polymer has to be soluble in the monomer. As you continue to polymerize, the system viscosity will increase with the degree of polymerization. So the larger the polymer gets, the more viscous or thick the solution gets. There are advantages and disadvantages to each of these, and I'll talk about those. When it comes to bulk polymerization, the purity is very high. You don't have a bunch of solvent or water or surfactant or other stuff in there, so you don't have to worry about removing it. So the only thing you really have to worry about is maybe removing traces of monomer. Therefore, you get really high purity polymer. It's simple and it's economical. You have two starting materials, you have a third product. It's good. You get excellent color and clarity too because the purity is high. Now the disadvantages. You only have monomer and catalyst at the beginning. You don't have any water or solvent or anything else to kind of control that heat and remove it. And this can cause autoacceleration, or what also is known as the Tromsdorf effect. And that is basically uncontrolled heat buildup that gives you a runaway reaction. I mentioned this before, but polymers are insulators, and so as you continue to build molecular weight in the polymer, it will insulate the reaction, it'll hold any heat that's present in, and monomers are often flammable. So you have a material that's holding heat in the presence of heat that is building in the presence of a flammable material. that could cause a problem. Now, I've had auto-acceleration happen to me in the laboratory when I'm using 25 grams. It makes a mess. If you do that when you're dealing with tons, you can have an environmental or health disaster. So controlling the heat of a polymerization reaction is not trivial. Also, you have to stir it. Chemical reactions are little tiny games of bumper cars. So functional groups have to be next to each other, so that propagating chain end, for example, has to be near a monomer for that monomer to add. If it's not there, if the monomer can't get to it because the solution is so thick, then it can't grow in molecular weight. So you have to stir that to make sure that everything is still available to react, and stirring gets difficult when your viscosity goes up and up and up. So that can be another challenge. Also, you need to get almost complete conversion, so greater than 80% to get, and that's hard to get when your viscosity is going up and when you have issues with heat control. So what you end up with is traces of monomer in the polymer, and again, monomer can be a toxic chemical. So this is a contamination in the final polymer. So solution polymerization. So this is not as simple. We have a suitable inert solvent, a monomer or monomers, catalyst, and polymer. That's what will be present in our reaction system. So heating and stirring is much easier. Everything is dissolved in a solution. So rather than it just being the bulk polymer that is created, you have a solution that keeps the viscosity lower. And that it's the solvent medium that accomplishes that minimization of viscosity. Also, you can do solvent reflux to get the reaction to happen. What that is, in other words, you boil the solvent, and that's your heat removal. That's the temperature at which your reaction will happen. You're not going to get out of control heat buildup or things like that. And through those things, you can get a very high conversion level. Now, that's all sounds well and good. However, you're using a large amount of solvent, and that is an added cost. And it's an added source of contamination. Solvent is a small molecule. It can get trapped in the polymer, and you got to figure out a way to get it out. So you have to separate everything, and that adds an extra step to the polymerization process. So extra steps means extra cost as well. Also, when you're boiling the solvent, that is the upper limit at which you can do the reaction temperature. So maybe you can put it under increased pressure or something, but the boiling point of the solvent is really the highest you can get your reaction temperature. So that limits that. And polymerization is a chemical reaction. It's a temperature-dependent process. The higher the temperature, the faster the reaction. The lower the temperature, the lower the reaction rate. So if you can get it hotter, then you'll typically polymerize faster. And time is money. So emulsion polymerization is also used, and this gets quite complicated. This uses water, a surfactant, and sometimes these are fatty acids or sodium lauryl sulfate, a monomer, a water-soluble catalyst, and your polymer, which is in latex form. So whenever you hear the term latex, it doesn't refer to the chemical structure, it refers to the polymerization method. So in other words, if you have a latex paint, it means the polymers present in there were made by emulsion polymerization. And these and what you create in an emulsion polymerization is particles, and these particles can be 0.05 to 5 microns in diameter. So emulsion polymerization produces latex products, and your polymer is entirely encased in these small particles, but even though it's in small particles, it can achieve very high molecular weights, on the order of, say, a couple million molecular weight. And you also get very narrow molecular weight distribution. So that you get very, very good control over your molecular weight distribution. Water, which is the bulk of this reaction system, is relatively inexpensive. Water is also a really, really good heat sink, so you're not going to get out of control heating. Because all of this stays at low viscosity, it's very, very easy to stir. And you can convert monomer to polymer at a rate of about 100%. But you've got a lot of other stuff present in emulsion polymerization. So the surfactant that you use to create these latex particles can be a source of contamination. And there's a whole lot of water there. Water is great to remove heat, but it's really hard to dry something. If you've ever been flooded, you know this. Drying, you can get wet real fast. Getting dry is the challenge. So you have to remove all that water. And that requires a lot of energy to do. Suspension polymerization is related to emulsion polymerization, as the same sort of materials. You have water, you have a stabilizer or suspending agent, monomer or monomers, monomer-soluble catalyst, your polymer product. The difference between emulsion and suspension, they're not a lot in terms of the advantages or disadvantages, but the particle size of the product in suspension is larger. That's 10 to 1,000 microns, where it's a lot smaller in emulsion. And your catalyst is soluble in the monomer in suspension as opposed to the water. So they both get really high conversion, but they both have the issues of contamination from stabilizers or surfactants, and then having to remove all of that water that you've suspended the reaction system in. So this concludes the second video of starting materials and polymerization processes. There will be a quiz on both of these videos, so please review both videos before you do each of your quizzes.